Allan has kindly offered to give you an update on what's happening at the City of Edmonton's Waste Management Facility, where there's going to be an addition of an anaerobic digestion component in the organics recycling program. So thank you very much, and Jolene, if you need to talk about the technical stuff, and then we'll scoot over to Allan, who has such a stalwart in terms of moving organics recycling forward.
All right, thank you very much, Susan. This is Jolene Rudder from Green Manitoba. We're happy to provide the technical webinar support here. If you have any questions, please hold them to the end, and then you can either raise your hand and I'll unmute you so you can ask the question yourself, or if you'd prefer, you can enter your question into the chat dialog box, and I'll read it aloud for you and have Allan answer it. And with that, Allan, if you would like to get started.
Thank you. This is a presentation on anaerobic digestion. It's an expansion of a presentation I did last month at the Alberta Regional Workshop, but I've expanded a bit for a national audience, and while the focus remains a bit on the City of Edmonton's project, I hope to provide some insight and ideas on dry anaerobic digestion systems in general and show how they might fit into an existing composting facility. So the way I've organized this presentation is I have a couple of slides on basic fundamentals of AD. Then I describe how AD and composting fit together. I'll jump over to our project and describe our 2 RFP processes. And then we'll take a look at some pictures of dry AD technologies, various aspects of them. And then we'll finish off at the end by trying to describe where we currently are at with our project. So I'm using the term fermentation here. It's a broader term that generally refers to the transformation of organic materials through the use of microbes. So it's mainly been used in food production, and it applies to whether I'm, say, making cheese in my own basement or what's happening in a cheese factory. But you can consider that composting is a fermentation process that occurs under aerobic conditions, whereas anaerobic digestion is a fermentation process that occurs under anaerobic conditions. For composting, as it's an aerobic process, essentially I apply oxygen here. I have my various feedstocks, the organic materials. It goes through composting, and I get a compost product out at the end. In terms of other byproducts, you get a release of water, but you also get released various greenhouse gases. A little bit of methane for some of the unavoidable anaerobic conditions you're going to get through your composting process. Hopefully most of it gets transformed to CO2, and you also get a little bit of nitrous oxide at the end. In contrast to that, anaerobic digestion occurs in the absence of oxygen. For those of us that work in waste management systems, we're kind of familiar with that because a sanitary landfill, properly operated, is basically the same thing as an anaerobic digester reactor with no mixing. A couple of byproducts that you get from AD is methane, and you can use that for renewable energy production, heat and power. You also get a solid material out at the end called a digestate. It's not as stabilized as compost, and to my way of thinking, it's not as attractive, but you can take that and run it through a composting process or a drying process to end up with a material that actually looks pretty good. I'm going to distinguish between high solids AD and low solids AD. High solids AD has been around for about 20 plus years, mainly in Europe, and it's geared more for more high solid materials like solid waste. We're typically talking about 15 to 20% total solids content, and it has a higher material structure, so you get greater porosity. In contrast to that, you have low solids AD, and it's been around a long time, and it differs from high solids AD and the way you pre-treat things, the processing equipment you use, the technology you use, and how you operated it. So low solids AD has been around for a long time. Back in the 1980s, I worked as a process engineer at the City of Edmonton's wastewater treatment system. So here are 6 digesters there, but those have been around a long time. Certainly the first four of them were built in the 1960s. And it's also been common technology around since at least the 1950s. So how AD and composting fit together? Well, I think it's a synergistic fit. I've provided 4 sort of fits there. If you're dealing with a lot of wet putrescible materials, such as a lot of food waste, it's going to cause you problems if you don't have enough porosity and enough drier feedstocks. So it may be better to deal with that material first by putting it through an AD process. Then at your back end, you can get your digestate product, and if you put it through composting, you're going to end up with a more attractive end product. But in taking some of the energy from the more putrescible waste, you can generate a digester gas, which you can then use for combined heat and power purposes. And there's also evidence to suggest, mainly from Europe, that it's going to compost faster in the end than if you take a raw feedstock and try and compost it separately. I draw your attention to a recent article published in the November 2014 issue of Biocycle that was co-written by Scott Gamble, one of our members on the board of directors of the Composting Council. I've also heard Will Britton of Woods End Lab give presentations on AD in the past. So as to why the City of Edmonton is interested in anaerobic digestion, well, we have a need to add additional processing capacity to our particular system. We have a limited footprint. We can't expand anymore on the site, and so this is a way to add some additional processing capacity within the existing footprint. And because we think that there's a lot of some ICI organics out there, and we think that most of it is food, we think it fits in that way too. Plus, we had a funding opportunity from this thing called the Climate Change Emission Management Corporation in Alberta. This particular slide gives you a little bit of background information on that particular corporation. Basically, within Alberta, it's a regulated environment in which greenhouse gas emissions are regulated. So there are about 100 plus industries that are regulated under a piece of legislation called the Specified Gas Emitters Regulation, and they basically have 3 options: to take actions on their own to reduce their emissions intensity, to purchase offsets from non-regulated activities, or to pay this $15 a ton into the provincial tech fund. And it's this corporation that administers all the money collected and gives out grants towards projects to reduce greenhouse gas emissions within the province. So we were lucky enough to get one of those grants. And if I go back to the next slide, this is our facility. Even though we manage about 200,000 wet tons of material per year, we no longer have any room for expansion, and we lack the peaking capacity, so that during the summer there's a lot of organics we actually do send to a landfill because we don't have the capacity to handle that. So also in terms of our project, what we're going to do is tack on an AD facility at the Edmonton Composting Facility site. We're going to send through select organic waste from both the residential stream, our peak materials, and source separated ICI organics from the commercial sector. So it's materials like that, sort of an idealized picture that we're after. And we're also going to send through some of the peak materials, largely grass that we get during our peak periods in the summer. We're going to generate a biogas that we're going to use for on-site combined heat and power generation. We're going to finish off the solid digestate coming through AD through our composting operation. We've sized our project at 40,000 tons a year, potentially expandable to 80,000 tons per year. In terms of city staff working on the project, there are sort of 3 of us playing various roles. Each one of the 3 of us are engineers. We have sort of specialized roles to play. I like to think of us as the triumvirate. It's sort of a historical reference to ancient Rome and the 2 triumvirates that successively ruled Rome in the last days of the Republic. So on our side, we have a money guy. He's the guy that's prepared our business cases. He did our grant application, and he's taken the lead in sort of doing various negotiations with our proponents. We have a guy who is the general supervisor of our engineering staff. So he's looking after things like putting out the RFP documents and keeping close track on the management of the project as it see its way through from design through construction. And then there's me. I think of myself as the ops guy. Back a lifetime ago in another line of work, I attended Canadian Army Staff College. One of the mantras of the day at that institution was the saying that amateurs discuss tactics, professionals discuss logistics. So I've always been focused on logistical things. If the goal is to get from point A to point Z, I tend to focus on how do I get from point A to point B, and then from point B to point C, and so on the eventual journey to Z. For this particular project, whatever we build in the end, I'm the guy that has to try and make it work. And then there are a bunch of other city staff that also work on the project, a couple of project engineers, and we have a construction manager on our side to see through the eventual construction. Also, in terms of what our project is aimed to achieve, when we did our grant application, essentially we told the grant funding agency that by processing 40,000 tons a year of material through AD, we can generate this much net power, this much net heat, and we're going to produce 16,000 tons of compost at the end. We will also reduce greenhouse gas emissions to the tune of about 43,000 tons per year. So in our process, we issued a request for qualifications, an open RFQ for technology providers back late December 2012 to January of 2013. We got 9 proponents that submitted proposals. We did evaluate them in terms of experience, what schedule they were going to provide us, how we thought the technology would fit, and then we did a number of reference checks. We shortlisted 3 technology providers. First of these was a firm called OWS. They were out of Belgium, and they have a vertical reactor, a continuous vertical reactor. Basically, you feed prepared feedstock in from the top. You take out digestate at the bottom. Second shortlisted technology was a firm called Viessmann Biofirm. They're more batch-type garage systems. So you've got sealed containers that are like garages, and you operate them successively. You draw off gas, you store gas in a bladder on the roof, and then use that to run CHP units. And this technology is based out of Germany. Third sort listed technology was a firm called Econ. It's also a batch type technology. The little nuance there is that a lot of their gas production comes from the liquid that they circulate through the solid materials, which they digest separately in secondary digesters. So we have 3 shortlisted firms. In terms of the overall project, we've been thinking about AD for at least 5 years. The opportunity came about. We were talking to our local educational institution, the University of Alberta, who was looking for some way to manage their organic waste. And then this Climate Change Emissions Management Corporation came out with a proposal call for renewable technology projects. We issued an expression of interest, or we submitted an expression of interest. We were short listed in December of 2012. We submitted a full proposal to the the grant funding agency. We went through our request for qualification process. In the end, the grant funding agency gave us $10 million of capital grants. And then following that, we secured our own funding, City of Edmonton and University of Alberta. We issued something in the end called the Design, Build, Construction Management RFP. It's a process that we used successfully in the past, wherein we end up with a contract with one firm sending us a proposal. They have other firms as subcontractors. So in the end, we're dealing with one firm, say a general contractor who has a technology provider as a subcontractor and an engineering firm as a second subcontractor. And we thought we were doing pretty good. The way the DBCM RFP works is we end up with firm prices for construction management, firm prices for engineering fees, and we end up with a target construction price. So we also at the same time issued a request for information for combined heat and power technology providers. We did that about a year ago. Our RFP closed. Everything came in over budget to the tune of about 135%, about 250%. So we had to cancel that RFP, and we were back to square one. And this is a quote I've used in the past. Things don't always go your way, and you sort of have to suck back and retool. So also from my previous background, a lot of the Western armies of the world have institutionalized something called an after-action review process, where they try to glean lessons learned so they can apply it to future endeavors. And it requires sort of a rigid formal process because there's a hell of a lot of difference between lessons observed and lessons learned. So hopefully we learned various lessons, and so about a year ago we started on a second RFP process. We decided to separate the RFPs for technology provider, and then issue a separate RFP for somebody to supply CHP equipment, and then we were using something called RFP process for the AD system supply. We were going to retain the design, build, construction management process for general contractor, and by doing these in sequence, we kind of came to the conclusion, well, this is going to take a longer period of time than we originally thought. This next slide, I'm going to describe a little bit about what we call the RFP process. The long name for it is it's a non-contract request for proposal process. That doesn't mean anything to a whole lot of folks, but you could also say that the NRFP stands for negotiated RFP process. And it's not quite bid shopping as what you'd get in the private sector, but a public tendering system, it's about the closest thing you're ever going to get. So we issued the NRFP late summer of last year. We received 7 proposals by the time we closed in October. We had our team evaluate the proposals, plus some reps from the University of Alberta and a couple of subject matter experts from elsewhere. We ended up with 5 shortlisted proponents for AD technology. Econ is a garage type system based out of Germany, so is Gecon. CompoGas is interesting. It's a continuous horizontal reactor system based out of Switzerland. Wiesmann was also a garage type system based out of Germany. Zero Waste is actually out of the States, but they have the North American rights to another German technology. And at the end of evaluating the proposals, we decided, well, we're going to make a number of reference facility visits. This is a key thing that we did. Essentially, you could have the written proposals in front of you, and you sit down and you read through them and you evaluate them, but you actually need to go visit certain places to find out what is the actual ground truth and whether some of the proponents sort of lied to you about various aspects of their technology. So we spent, 2 of us spent 3 weeks in late 2014 and early 2015 going through these reference facility visits. And at the end of the day, we came back, we re-evaluated the proposals, ranked them, and this is where the NRFP process kicks in. We rank the proponents, and we're allowed to negotiate with the top ranked proponent. We can't do a deal with them, then we go on to number 2 and so on, until eventually at the end we come up with a deal. So I'm going to skip back to take a look at the technology of dry AD systems. Some of them will run at mesophilic temperatures, some of them will run at thermophilic temperatures. The continuous flow systems are mainly they get the feedstock into a liquid form. You get typically better gas production than you would with a batch type system, typically on the order of maybe 130 to 200 cubic meters per ton of feedstock, depending on what that feedstock is. The batch type system is you're making individual batches in garages. Some of them will get use secondary digestion of the liquid percolate to get additional gas. But the energy balance is better if you want to run it in a thermophilic operation with a batch type system than you would get with a continuous flow system. So now I'm going to go through a series of photographs of some of these things. I was concentrating first on variations in feedstock. This material, it's a little hard to see from the photos, but we thought in the end it was a little bit too dry and a little too much a yard waste in the form of leaves to get the gas production that you want. And the system that where we saw this, that was true. They were only getting about 65 cubic meters per ton of this feedstock. Another system we saw, well, we were thinking that this stuff is too wet, plus it had too much plastic film contamination in it. You can see sort of the leachate from that feedstock sort of draining on the floor, and then also in another location where we saw a lot of this wet feedstock. They didn't quite have the controls on the tip floor, and there were a lot of seagulls getting at the material. And this material we thought was too wet. Other facilities, we thought it was just about right in terms of how dry the material was, the lack of other contamination. And so we thought that was just about right in terms of feedstock for dry AD. Then there was another facility. I was standing in one location looking at a row of feedstock. I took the picture to my left. This was separate, or the organic residues from a dirty MRF was being sent to this AD facility. This is commercial SSO, sort of just to the right of that first picture. And then to the right again, there was a lot of yard waste coming in. So there are wide variations in the supposedly SSO feedstock that this one facility was getting. In terms of nice looking plants, we saw a couple of facilities where a batch type system, all the anaerobic digesters fit in one particular building. To the left of this picture here, staff facilities at one end of it, CHP facilities next to it, and a separate percolate tank. And then they also made use of the attic space. And in the attic space, that's where you collected your percolate. You also collected your gas, and you had rooms also in that attic space where there were the controls for this thing. Another facility, the percolate tank was sort of integrated with within the building itself. And in the attic space of that facility, they also have their ladder for gas collection right on the roof. A couple of more locations, we saw a facility that had a double bladder system directly out in the open on top of the roof. This facility was in California, so we were thinking in our climate it wasn't going to work. Saw another facility where the percolation piping was undercover, but the gas collection was in the open. They also had some of the gas treatment facilities on the roof. Here's a biofilter, a round biofilter, built right on the roof. I thought that was kind of neat until I asked them. This is a look at the biofilter media with the cover on top of it. I thought this was pretty neat until I asked them how were they ever planning to replace the media when they had to, and the answer came back, well, it was at that point it was looking like guys with shovels. This is a picture of a continuous horizontal flow reactor where you have these 3 horizontal reactors that are rectangular tanks sharing common walls placed next to each other. And each one of them had a central shaft that sort of stirred the contents of the digester. And this gives another view of how long these particular digesters are. In these continuous flow systems, you do have to look at dewatering your digestate because it's in a wet slurry form. So they were taking material out of the back end of the digester, pumping it out to a separate building here where they were dewatering the material, They were using screw presses at this particular facility. So these are the screw presses here. Here's a picture of the press screen for the screw press. A picture of the dewatered digestate, and then the screw press water that came out as the liquid material. In garage type systems, you get variations on the types of doors that you have and how they get sealed. This particular system here, it was simple and robust, but the door technology hadn't changed in over 10 years. So these doors sort of swing open like an awning. And then other systems had different doors and also variations on the way that they sealed these doors. Apparently, some of these technology providers have patents on the way that they seal their doors. We saw variations on how the percolate was draining through the materials. Some systems we saw floor drains. There were issues with those particular floor drains. There's a buildup of salts within the drains in the floor. You get an eventual buildup around the pipe until this plugs off. Some of them have, some systems have tried to go with wall drains instead to try and mitigate that. And then we saw some issues with secondary digestion. Both systems that we saw where they did secondary digestion of the percolate material in separate tanks. Because they were counting on the gas coming from the secondary digestion, they needed to maximize the surface area for the microbes to grow that would generate the gas. So they were using a plastic media similar to what you'd get in a trickling filter or an ammonia stripping tower. And both these systems had issues in that the plastic media was plugged with salt. And then once that occurred, it was a hell of a job to try and salvage and recover the plastic media. One of the things we were looking at was how well these systems integrated with composting. Here's an example. We think of a pretty decent integration here. So the feedstock came in to this hall. There were 8 of these digestion units here, and then a further 2 aeration boxes. So once the material was finished digesting, they took it out with the front end loader, put it in the aeration boxes, and then spent a couple of weeks to adapt the microbes to an aerobic environment again. Then once the material dried out a bit in the aeration boxes, they took it out and put it through a gore cover system. Wasn't a standard gore system in that they didn't go to the full regime that Gore recommends. It spent about 4 weeks under the Gore covers. Then they took it to a covered hangar where they finished curing the material. And then they screened it at the end using a standard Comtech multi-star screener. Another good example of integration with composting there, they took their digestate, put it into an in-vessel reactor, and that included a curing. Then they took the finished material, sort of screened it in this building here using a Comtech multi-star screener, and then went into this second building where it was screened through a Dopstat trommel, and then they bagged the material and palletized it for distribution. An example of something that's not that great an integration with composting. This is a facility that took a lot of contaminated feedstock. They first fed it through a manual picking line. Then they took that picked material, fed it into the digesters. It came out the end. It was still sort of ugly looking stuff, but it was going to go into an aeration boxes. And then once it came out of that, they fed it through a disc screen again. And at the end of the day, only 30% of that material ever made it to composting. The rest of the stuff went to landfill. And then a final example, to my way of thinking, this is a totally misguided attempt at combining composting with anaerobic digestion. It was a functioning composting system. Christian's brothers tunnels. They tacked on AD onto it. They tried to percolate through these tunnels. While the tunnels were kept going with their aeration, and then they tried to take that percolate, digest it in a secondary digester. But they ran into problems with poor percolate distribution, and I was thinking, no wonder, you can't sort of suck and blow at the same time here, which is what they were trying to do. And at the end of the day, it was an MBT plant, so they were just trying to knock the organics out, and they sent the compost in the end to be landfilled. So next couple of slides, I'm going to talk about gas management. Once you generate gas from an AD system, what options do you have? Well, there are basically three. You can use it to generate combined heat and power at your own site, and if you're going to use it yourself, then you save a lot in terms of not having to distribute and to transmit that power. You get better overall energy efficiency. Your second option with the biogas is to use it to fuel vehicles, and for those in the waste management business, there's a certain charm to that, and that you can demonstrate. Here's a closed loop system, and I've seen it in landfills where you take your landfill gas, and instead of generating power, you clean it up to the extent that you can fuel your collection vehicles. Your final option is to get it to pipeline quality to feed into the natural gas grid. As you go down this line, there are more things that you need to do to condition your gas to that particular quality. And this is what I mean by terms of greater energy efficiency. If you're taking power from off the grid, only 40% of that, you only get 40% of efficiency from the fuel that you input, whereas if you're producing both combined heat and power, you essentially can double your energy efficiency. So if you're going to generate biogas from AD, the components you need to look at is some means there's a flare at the end. You need to condition that gas. Then you need to generate heat and power. So you generate power by taking a couple of engines, connecting them to transformers to generate power. And then you do heat recovery at the end. Typically, you'll put a jacket around your gen set, and you may also do stack heat recovery by putting a stack economizer at the on your exhaust stack to a water-to-air heat exchanger. So in terms of gas storage and flaring, here's an example of a double-bladed or a gas dome there. And another modular AD system, again, where they had the a dome on top of the digesters. You always need a flare at the end, and here's an example of a flare here, because AD system isn't something you can instantaneously turn off and on. If you're doing repairs, you're still going to be generating that gas, so you need a flare to flare-off digestion during periods of system maintenance. Packaged CHP units typically come packaged within sort of shipping isotype containers. Your engine's on the inside, you have heat recovery on the outside. A couple of examples of that. And then an actual picture of an engine within one of these containers. You need to condition your gas to make it usable. For CHP, the standard is always chilling, so you can take out some of your most of your particulates, some of your VOCs through chilling, and then you typically put it through activated carbon. Take out some H2S and some other volatiles. Another example here of a chilling system, a powder activated carbon unit. Third example of a chiller and PAC again. And some systems, if they have a lot of H2S, they'll use a large number of powder activated carbon units in a series. But if you have a lot of H2S, where it's no longer economical to keep replacing your activated carbon, you may have to do something else. So this is an example of a biological desulfurization unit, and it's essentially you're passing your biogas through a stripping unit where you have a mixed culture of microbes that will absorb the H2S and convert it to elemental sulfur. Here's the control for that particular system. Or you may have to use something else again. This is an example of a ferric chloride system. So you're adding iron salts to react with the sulfides to form insoluble iron sulfides that will precipitate out so that H2S can't form. And if you're going to bring it to eventually the pipeline quality, then you need to go to something else again. This is an example of an amine scrubber within a isotype container, and that's a common gas sweetening process where you're using various compounds called amines to sweeten the gas, and essentially take out both your H2S and your carbon dioxide. Another view of the same unit, and there are also a couple of activated carbon units at the tail end of that. So if I come back to our particular project, where we are with our project is we re-ranked our proposals. We've had our negotiations with our #1 ranked proponent, and our money guy was sort of key to that in the way he was trying to squeeze the proponent, but we got through that process. We issued a letter of intent to them. So we sort of have a deal. We have our kickoff meeting actually tomorrow, where we need some outputs from them to finish off the DBCM RFP in order to get a general contractor and an engineering firm on board. We're thinking we can get that out this spring and award by late summer. We're also working on another RFP package for supply of CHP equipment. We're also targeting to get that out this summer, and then the detail work comes after that. As other things that we have going on, we have to apply for an environmental approval from our provincial regulators. So there are some of us working on that. And we have another capital project going on at the same time to try and find another cure site, because we've got all this stuff that's going to come out of AD, and we need space to cure it, turn it into compost at the end. Picture of our current cure site. We have 15 hectares there, but we're out of space on site, and we had to go back to mass beds that were turned by this particular turner, whereas we really want to cure the stuff more in windrows, turned by a windrow turner. So basically where we are at our in our timelines, we have late this year to start some construction, finish it off through next year. Team affects construction pricing when we go to tender. And I'm going to close off this presentation with a couple of pictures here. This is our existing facility looking sort of south. When we tack AD onto it, this is what we think it's going to look like. So that's the presentation, and I'd be happy to take some questions. Thank you.
Thanks very much, Allan. Your leadership continues to flow, and very grateful for your sharing such detailed information and knowledge, and certainly your direction as to the development of the Compost Council of Canada certainly reflects the combined effort of both composting and anaerobic digestion. So thank you for that. I'll turn it over to Jolene to manage the questions.
Thank you. Thank you for that as well, Allan. Lots of great pictures in there. We do have one question from Vahid. How do you expect to see benefits from adding digestate to the composting process?
We think that out of the aeration boxes, we're going to get material that is ready for curing. And then we can take it out to a cure site and cure it as compost. We may need to add a bit more carbon to it in the form of wood chips, but that in the end is what we're trying to achieve.
Will it affect the nutrient quality or any other parameters?
Not that we know. We think from the results we've seen, the end compost coming out of AD is going to pretty much be like regular compost, where you compost it right from the start.
Okay. And next question from Jeff Hill. How will the AD material hit the pathogen reduction requirements?
The AD material won't. We hope to get some pathogen reduction by putting it through the aeration boxes. If that's insufficient to pasteurize the material, we have an entire curing stage that we go through, and the material will be pasteurized in the end. With AD processes, there is no inherent temperature rise. So we're counting on composting to pasteurize the end material.
So it pretty much has to go through the whole process then?
Yes, we need to compost it at the end to turn it into a compost that will meet CCME compost quality guidelines.
Okay. Just a couple follow-up questions here. I'll go with Jeff Hills. Are you going to use windrow or aerated static pile for composting?
We hope to use windrows. We've found with composting MSW in the end, because we go through a number of separation steps, screening, we get better porosity and better curing of MSW compost in windrows than we do in mass beds.
All right, and then back to the first question, sorry, about adding wood chips. Would the wood chips be added afterwards or prior to adding it to the AD?
That's a technical question we haven't, we don't have the full answers to yet. We've sent material off for testing. to the old Alberta Research Council in Vegreville. They're telling us that to get the right porosity for digestion, they needed to add about 5% wood chips in at the beginning. Our technology provider has given us a design that says they don't think they need wood chips added at the beginning. They think they need to add it in at the aeration stage after the material has been digested. So it's one of these technical questions that we hope to resolve within the next month, because that a lot of the design depends on having that answer.
Okay, and here's another interesting question from Aaron Jensen, and I think it kind of goes in with another follow-up question. I'll try here. So how long does it take for the aerobic microbes to take over from anaerobic microbes, or is there any other malfunctions or anything like that expected from adding digestate to composting?
In terms of digestion, the system we're going with has batch digestion for a 2 to 3 week period. And then following that, the period of aeration is probably another week. We need to dry out the material a bit and also acclimatize the microbial population to our aerobic conditions. And then following that, the great hope is the material will take a shorter time to cure than our regular compost does.
Okay, we must have a few microbiologists on this, because another microbial question, paraphrasing a bit here, but because of the anaerobic process, how does it affect the microbial abundance, and will this affect the overall quality of the end product?
We don't think so. From the various facilities we've seen that turn the material into compost at the end, you end up with regular compost.
Okay. Next question from Serge. Is there pre-processing or of incoming